We are going to be talking about section 2.2, limit of a function and limit laws. The first example, actually we have two here, and I'm going to go through both of them. The first one, as you will see, there's a hole here. The second one is just this hole is filled in. These two are different functions, and this function is not defined at x is equal to 1, but this function is defined everywhere, including 1. This is a line with an empty dot here, and this is a line, a continuous line. Okay? Let's go over this just a little bit. I have just some extra writing here. Let's see, that's all. Okay. Okay, so this one is the graph 1. This is the graph of f. Here, the denominator can never be 0. So this is the function f. The denominator shouldn't be 0. It is 0 at 1. That's why this function is not defined at 1. Okay, observation, f of x is not defined at 1. Graph 2, it is this line. It's the graph of g. I called it g. It is the same graph as the graph 1, but we have this one dot is filled in. I want you to observe this. Actually, if you start with f, okay, let's start with f. I'm going to write that here, f of x. Okay, actually you can get to g as follows. This is our f, and you're going to factor it out. You can factor this x squared minus 1 as x minus 1, x plus 1. And then x minus 1s are going to cancel, and then we get x plus 1. This x plus 1 is our g. Okay? So, we can actually define g as follows in terms of f as well, because we got that g using f, simplifying f, right? So g is the same as f whenever x is not 1, but g is equal to 2 whenever x is equal to 1. So they only differ, these two functions only differ at x is equal to 1. Okay. Next page. This is the same function f, and we want to see what happens as x approaches to 1. So we build our table where, we can see this on the graph as well, but we want to see it on the table too. We just select numbers that are close to 1. For example, 0.1, 1.1, 0.99, 1.01, 0.999. These are all close to 1 numbers. Okay? And then we find the corresponding value of f. These are the f values corresponding to these x values. Then I want you to look at these values. These values are close to 2, right? 1.999 is close to 2.01, it's close to 2, etc. So this is showing us that as x gets closer to 1, f of x gets closer to 2, and this is the same thing in here. As x approaches to 1 from the right or left, either way, f of x approaches to 2. Okay? And here we have three different functions. Okay, this function we've seen it. This is f. And we just want to define at x is equal to 1. This is not defined. Let's define it something else instead of 2. Let's define it 1. So this is another function. Okay? And the very last one, which we called it g in the previous one. Okay? It is at x is equal to 1, we define it at 2. Okay? So let's see what we had written here. Okay? No, these functions are looking similar, however they are all different. Later we will call f and g as discontinuous functions, whereas h is a continuous function. Okay? See, why is that? Because you can just start here and continuously draw it without removing your hand. But here you cannot do that. You come down up here, you have to jump down and then come back again and then go there. So you have to remove the pen when you are drawing it. Here, similarly, when you're drawing it, you come to here till here and you jump, and then you continue drawing. So these two functions are not continuous, but this is a continuous function. We will discuss this more later on. And here you can see okay, there's a typo here. This is not, I mean, this, sorry about it. This is an no typos. This is an identity function. Y is equal to x. Whatever the x value takes, y value takes the same. This is the identity function, and we have the constant function. These are all continuous functions you will see later on. And the limits are just very simple. As x approaches to c, the limit is c. And as x approaches to c, the limit is k here for the constant function k. Okay, these are three nice functions that we want to talk about. In the first one, this is step function. Look, it's like a step, this and up here. Step function. And it is defined as follows. Let me make it a little bit bigger for you. Okay, here, whenever x is less than 0, it is 0. But x is equal to 0 doesn't include, it's empty here. Okay. And whenever x is greater or equal to 0, it is 1. Okay, this is a piecewise function. We call it unit step function because it is defined 1 here. Unit comes from the value of 1. And let's see what I had written here for you. Okay, right limit at 0 is 1, left limit at 0 is 0. We say that the limit at 0 does not exist. Okay, so right limit at 0, we approach from the right, the limit is 1. We approach from the left, the limit is 0. So they don't match. So we are going to say the limit at 0 does not exist. Let's get this butterfly example. See, this is butterfly and a dot here. Do you see that? So this is just a little bit different function than the butterfly we introduced at the beginning of this class. So how do you define it? Whenever x is not 0, this is the butterfly function 1 over x. Whenever x is 0, you define it to be 0. That's okay. So this function is defined everywhere now, because butterfly function usually is not defined at 0. Okay, so let's see what I have written here. Here, right limit at 0 is infinity, left limit at 0 is negative infinity. We say that limit at 0 does not exist. Look at that. When you approach from the right, the limit is going to infinity. When you approach from the left limit goes to negative infinity. Right limit and left limit, they don't agree, so the limit doesn't exist. Let's look at this function, which is again piecewise function. Until 0, it is the 0 function. After that, it's the sine 1 over x function. And at x 0, it's not defined here, right? Okay. And let's look at the right limit and left limit. Let's see here what I had written. Let me put it away. If you look at this right limit at 0, it does not exist because it is going up and down, no one value. It's not a unique value, it's going up and down, it is oscillating. We call it oscillating, okay? Oscillating up and down. And left limit at 0 is 0 because it's the constant function 0. We say that the right limit and left limit, they don't agree, so we say that the limit at 0 does not exist. Okay? That's how these functions are. Now let's get the limit laws. The limit laws are, we have a sum rule. If you have two functions with the finite limits, L and M, then their sum will be the limit of the sum of two functions is going to be the sum of the limits. And difference of the limit of the difference of two functions is the difference of the limits. And constant multiple rule. If you multiply a function with a constant k, the limit as x approaches to c is the k times the limit of the function f, which is L. Product rule is also okay. Limit of the product is equal to product of the limits. But this is going to be true if you have both of the limits exist, for L and M exist, which means they are finite. There's a quotient rule, and limit of the quotient of two functions is ratio of the limits, L over M, but be careful that we don't want M to be 0. Okay, and we have a power rule, which is limit of the power of a function and power of a function. Let me make it bigger just a little bit. Okay, power of a function, and if you take the limit as x approaches to c, is going to be equal to the nth power of the limit of f, which is L here. Of course, we assume here n is a positive integer. And then we have the root rule. If you have the nth root of a function, and if you're taking the limit of that, you can move this limit inside the root function. So it's going to be the answer is going to be the nth root of L. So this is really nice property. You can move this limit in and out. Like in here, you can move this limit in and out of this power. Okay? Okay. Here, be careful here. Nth root, if n is even, we assume f of x is greater or equal to 0. Otherwise, it doesn't make sense, right? Because square root, for example, square root of a negative number doesn't make any sense for us. Okay, let's look at the polynomials. For the polynomials are always nice functions, and the limit of the polynomials are you just plug in the value and that's all to it. So x, you just plug in power p polynomial p of x. The answer is p of c. You just plug in x by c, and that's it. So let's see what I had written here. Polynomials are nice functions, and if you want to, okay, they are really nice functions. Okay, to evaluate their limits, we just plug in the value of the x in the expression. That's all to it. Okay, let's move to the next one. Limits of rational functions. Rational functions, if you remember, it's the polynomial over polynomial. Okay, we talked about this before. And how about the limit? As x approaches to c, you just plug in the values c for x. However, be careful, we don't want q of c to be 0. If q of c is 0, then it's a different story. Okay, let me see what I had written here. Rational functions are behaving nice, except at the points which make the denominator 0. Yeah. Later we'll say that they are continuous everywhere except at the points which make the denominator 0. So they are almost as nice as polynomials except the denominator. Okay? Okay. So next, you can see two examples here. Let me make it smaller now. Okay, let's see. Okay. So we have two examples here. Actually, they are graphs looking alike, right? So this intersects at -2, and this is like 1 to 3, the same picture, except we have the dots filled in here. Okay, here it's not filled in. This is like a butterfly function, but shifted, kind of shifted, okay? Okay. So what's the relationship between these two? The formulation is looking more complicated than this one, and I'm going to explain the relationship. Okay, let's look at this explanation. So I gave the name capital F for this one. F of x is equal to x squared plus x minus 2 over x squared minus x. This capital F of x is well defined everywhere except at the points 0 and 1. At 0, no value for it, and at 1, it's empty. Okay? And we can say that f of x is undefined at x is equal to 0 and 1. Let's look at the right limits at 0. Right limit at 0 is plus infinity, and left limit at 0 is negative infinity, and limit at 0 does not exist. And we are saying f of 0 is undefined, moreover. How about right limit at 1? It is 3. When you get close to it, it is 3. What's the left limit at 1? It is 3 again. So the limit at 1 is 3. However, f of 1 is not assigned any number, so f of 1 is undefined. Later, we are going to say that this function is not continuous at 0 and it's not continuous at 1, but it's continuous everywhere else. We can say that, but it is continuous everywhere else. Okay, that's all we want to say here. And there, let's see, let's look at this one, this explanation. Now, there's a relationship between this capital F and capital G, you will see. Okay, here is the example 2 I meant. Let me make it a little bit smaller from the right so that you see it. This example 2 is G. G is x plus 2 over x. We want to observe something. I told you there's a relationship. Actually, we can get G from F as follows. You start with F and you're going to factor it out. X minus 1, x plus 2 over x minus 1 times x. And then we have the common factor, x minus 1 and x minus 1 here. So we can factor it out. We cancel like terms and we get G, x plus 2 over x. Although we get g of x from f of x, g of x and f of x are two different functions, very important, okay? Two different functions, as you see the graphs as well. I have written some notes here. Gx is well defined everywhere. Look, Gx is well defined everywhere except 0. Okay, Gx is undefined at 0, you can also say that. And right limit at 0 is infinity, left limit is negative infinity, and g of 0 is undefined. And how about 1? Right limit at 1 is 3, left limit at 1 is 3, and limit at 1 is 3. Okay, and g of 1 is 3, it's well defined, so all is good except 0. Later we will say that g is not continuous at 0, or we will say that g is continuous everywhere except 0. You can also say that, okay? Alright, so let's close this. Okay, let's look at this function. Let me see what I've written here. We are going to solve this on OneNote. Okay, I'm going to make OneNote available for you. So, let's see. Okay, so I'm going to open up, let's see. I'm going to open up this, okay? So we are talking about, let me see. I must have drawn somewhere. Not highlight, and draw here. Okay. I want to use this, okay. So here, f of x is given to be what? Square root of x squared minus 100 minus 10 over x squared, yeah? Okay, what's the question? In the question, we're going to find the behavior of f near 0. And you can build a table like that. When you build a table, for example, choose points that are close to 0, like 0.51, 0.1001, and you get these numbers, and these numbers, as you would see, they approach to 001 and 005. But if you take smaller values that are close to 0, look at this. Maybe it's approaching to 0, but which one is correct? Okay, that's the question. So how would you answer that? Maybe we should do some extra work, okay? So what's the limit as x approaches to 0 for this? Okay, f, that's the question. So we have a trick here, okay? We are going to multiply with the adjacent, conjugate, not adjacent, conjugate of that. So what's the conjugate of this? Let's see whether it's gonna work or not. Okay, the conjugate of this is gonna be, okay, plus of this. Okay, you just change this. Okay, this is plus, this is the conjugate, and you multiply numerator and the denominator with it. Okay, so I have x squared here, and then x squared square root of minus 100 minus, sorry about that, 10 and close it. Okay, and then this is going to be equal to, let's multiply this out, you get x squared minus 100. Okay, I think it's plus, let me see. It's plus, not minus, sorry. This should be plus, otherwise it doesn't make sense. This is plus, this is plus, alright. And then let's go back to here. We're squaring it, plus minus 100 over, these are going to cancel each other. Now I have x squared down here, and then this expression here, okay? Alright, so let me go down if I can. Okay, let's see, why does it work? It's refreshing. Okay, then let me erase some parts to gain some. Okay, I'm going to erase this part so that I am going to have some room. For some reason I can't go any further. Okay. Okay, so after I did that, so what's the limit of this? I'm going to go back to here. So I'm going to say limit as x approaches to 0. I have x squared over x squared times that. So I'm going to erase this x squared. Let me write that. X squared over x squared times square root of x squared plus 100 plus 10, right? Okay. Now, these x squares are going to cancel. Okay? So I have this left, which is, maybe I should write it here. Let me read that. Okay, so this is going to be a limit as x approaches to 0, 1 over square root of x squared plus 100 plus 10. Now I can plug in 0 because it doesn't cause any problems. So if you plug in 0 here, you get square root of 100, which is 10. So my answer will be 1 over 20. But 1 over 20 is what? Okay, this is 5 over 100, which is actually 0.05. So this is the limit. Okay? So this is the limit of the question. Okay? So that's how we would do. Okay, so this is the right answer. Okay? Alright. Next we want to talk about the graph of f, which is the sandwich between two graphs, f and h and g. If you have a function, blue graph, squeeze between the red and the yellow graph, and if you know the limits of the h and g as x approaches to c, can you say anything about the limit of the f? And actually there is an answer to it, which is the sandwich theorem. When you have g, f and h ordered like that, in other words, f is squeezed between g and h like that, and for all x in some open interval containing the point c, that, and also if we assume that g and h, they have the limits as x approaches to c, and if they are the same, they have the same limits, L, then the limit of the function between these two functions is going to have the same limit, L. Okay, here's an example. Let me make it a bit smaller for you. Okay, so we have the function u here. We have 1 plus x squared over 2 and 1 minus x squared over 4, and u is squeezed between the two. And we ask the limit as x approaches to 0. So we look at the limit of this as x approaches to 0, this is 1, and as x approaches to 0, this is 1 again. So the limit of u in between is going to be the limit 1 as x approaches to 0 by sandwich theorem or squeeze theorem, they say. Okay, here's another example. So let's say we have the blue function that's squeezed between the absolute value of theta and absolute value of negative theta. You know the absolute value function, right? And what would you say about the limit of the sine theta when x approaches to 0? So I have some writings here. We have to recall a useful inequality, which is minus absolute value of x is less or equal to sine x less or equal to x, absolute value of x. We know that the limit as x approaches to 0, this is 0. Also, this is 0, limit as x approaches to 0. By sandwich theorem, limit of sine x is 0 as x approaches to 0. Okay, this is reasonable. Let's look at this three functions. So I have the 0 function, I have the absolute value of theta, and I have this 1 minus cosine theta. And what's the limit of this 1 minus cosine theta as x approaches to 0? That's the question. You recall again the useful inequality, which is 0 is less or equal to 1 minus cosine x less or equal to absolute value of x. And limit goes to 0 and limit goes to 0 by the sandwich theorem. The limit is 0 as well. Okay, let's move on. We skip section 2.3. In section 2.4, these are the one-sided limits. Okay, here's the first example. Let's see. We solve this on one note. This is the x over absolute value of x. Let's go to it. Okay, I'm going to erase this first. Okay, let's see. Let's go up a little. Okay, so the question was one-sided limits of the function f of x, absolute value of x over x. Okay, this is an interesting function. So I want you to observe that recall, maybe I should write somewhere here, recall, okay, absolute value of x is equal to x whenever x is greater or equal to 0. It is negative x whenever x is strictly less than 0. So we use this. And then this is going to tell us that f of x is equal to, okay, x over x whenever x is greater or equal to 0. It's going to be negative x over x whenever x is less than 0. Okay? Maybe I should erase 0 because it's 0, it is not going to be meaningful. Okay? It's 0, it is undefined. Undefined at x is equal to 0. Okay? Let me erase that so that you don't see this like that. Okay? Now, but what does this mean? This means f of x is 1 when x is greater than 0. It is negative 1 when x is less than 0 and undefined at x is equal to 0. Okay? So, this is what we have now. And the question is, how would you draw the graph of this? Actually, the graph is exactly this. Look, whenever at x is equal to 0, it's undefined. X greater than 0, it is 1. Look, when x is less than 0, it is negative 1. Look, this is the graph, okay? And what is the right limit? Right limit is 1, left limit is negative 1. So let's write that. Okay, so right limit limit is 1, left limit is -1. So limit, whenever they don't agree, right limit and left limit, we are going to say does not exist. This means does not exist. Does not exist. Okay? So that's the solution to this question. Alright, so let's move to the next one. Okay, let's get this function. Let's see what I had written here. Okay, we saw it on OneNote. Look at this semicircle. This semicircle, let's look at the right limit at 0. Pardon, let's look at the limit at -2 and 2. Left limit at 2. Okay, let's look at that. Actually, this is obvious. So maybe instead of going to OneNote, we can just talk about that. This function, when you approach from the left, this goes to 0. So the left limit at 2 is 0, but right limit, the function is not defined there. Okay? And right limit at -2 is 0 again because it's going down to 0. And that's it. So we have the one-sided limit. So we have only right limit here. We have only left limit here. We don't have the right limit at 2. We don't have the left limit at 2. The reason is the function is not defined there, okay? If you plug in 3, for example, this is undefined. So because of the domain, you cannot talk about that. You have the one-sided limits. Okay, this theorem says we are going to say f is going to have a limit at the point as x approaches to point C if left limit is L and right limit is L and they agree. They have to both be the same number, which is L. Okay, that's what I told you before. So this theorem states that. Okay, let's see. So what's this graph of the function? Let's look at the points. Okay, for example, at 0 we have the right limit, which is 1. At 1 we have the left limit 0, right limit 1. They don't agree, so at 1 we don't have a limit. At 2 we have the left limit 1, right limit also 1. So at 2 we have the limit 1. At 3 we have the left limit 2 because it is going up until 2, so this height is 2, and the right limit is 2, and so the limit is 2 as x approaches to 3. Here we can only talk about the left limit, and the left limit is it 1 or this thing? I think it is 1, right? Because the behavior of function is going down, so the left limit is 1. Okay. Okay, I want to say something about this picture as well. So this picture kind of familiar to you because before we have seen like a 0 function here and then this oscillating function. But actually this function y is equal to sine 1 over x is looking like that. Look at that, it's just getting closer to 0 and oscillating, going up and down, up and down, up and down. It's similarly here, going towards left, getting close to 0, up and down, up and down. So what about the limit as x approaches to 0? This is an oscillating function. It oscillates up and down as x approaches to 0. Maybe I should say that. As x approaches to 0 from either side. Okay. Right and left limits do not exist, hence no limit value at x is equal to 0. Okay, this is it, done. Alright, so this is a special function you will see in the exercises. Let's close this. Let's look at this sine theta over theta. So this is an interesting function as well. The previous one was sine 1 over x, so they are different. Okay, this is sine theta over theta. This limit exists, but this limit doesn't exist. Okay, they are two different functions. And sine theta over theta, as you would see in the picture, from the right it is 1, from the left it is 1, so the limit is 1. Okay? So this is special. So we actually give this as a theorem. Limit of the ratio sine theta over theta as theta goes to 0. Limit theta goes to 0, sine theta over theta is always 1. Here theta is in radians. Okay? This is kind of geometric proof of that. Yeah, so I want to stop here, and then I will continue 2.5 in the next recording.